So hello and welcome to the operating system class. So in the introductory part of the deadlock, we have seen that there are four different methods to handling a deadlock. So the first method that we have seen is the deadlock prevention. Then we have seen the deadlock avoidance, deadlock detection and recovery, and the last one is the deadlock ignorance process. All these processes are uh, in their place. They are very good method for handling the deadlock. So we'll see one by one. Like the first one is the deadlock prevention. And the prevention says that we'll put the measure into the system in such a way, or we put the algorithm, the deadlock prevention algorithm in such a way so that the deadlock will never occur into the system. So we impose each and every request done by the process about the resources, and we'll filter it and we'll see the conditions. If that is satisfied, then only we allow those processes to have those resources for the further execution. Now, the second one, the deadlock avoidance, is a lazy approach than the deadlock prevention. Here, what we are having is we are maintaining the condition such a way so that we'll put the condition on the new request that is entering into the system, and we'll see whether after fulfilling the request of that new process, my system will be in a safe state or not. If it is in a safe state, then we'll allow that particular process to execute. Then the next one is the deadlock detection recovery. Here what will happen is we don't have as such the prevention technique or as such the avoidance in technique. It means that whenever a process come to the system and ask for the resources, we'll allow it. And without doing the pre-checking, we just allow it. But once my system go into the deadlock and my system is detected that there is a deadlock, then only I can go for the recovery process. So this is another lazy approach that is used here. Next one is the deadlock ignorance. This in this we assume that in the system never deadlock will occur. Means the system is so robust that the deadlock is not going to occur into the system. So that is the philosophy behind deadlock ignorance. Okay, so we'll see one by one the definition for that. The first one is the deadlock prevention. It designs such a system which violate at least once if of for necessary condition of deadlock and ensure independency from deadlock. So in this, what will happen is the deadlock prevention. Now we know that there are four necessary condition for deadlock, right? So if these four condition will be occurring into the system, then only my system will go to the deadlock. And what are those necessary conditions? So we have seen in the last class, those necessary condition is this one. So we have the first one is the mutual exclusion, second one is the whole and weight, third one is the no preemption, and the fourth one is the circular weight. Now prevention says that if we able to remove or violate any of these conditions, let's say this condition, and this condition is satisfied, but somehow we are violating this condition to occur into the system, so my system will never go into the deadlock. So that is the philosophy behind deadlock prevention, that any of the condition you make sure that it will not satisfy, so that my system will never go to the deadlock. That is the prevention technique. So here we apply the algorithm in such a way so that my system will never go into the deadlock. So it says that the design will design such a system which violate at least one necessary condition of the deadlock and ensure independency from the deadlock. Now here we use lot of algorithm to do that. Means we can pick up any of the necessary condition and will apply the algorithm in such a way so that that condition is never going to occur into the system. That is the philosophy behind the deadlock prevention. Okay. Now the next one is the deadlock avoidance. Here it says that the system maintains a set of data using which it takes a decision whether to enter a new request or not to be in a safe state. Now, in the deadlock avoidance, we avoid the deadlock in such a way so that my system will never go into the deadlock. So here we'll not use so much complex algorithm. Here we'll use some light algorithm. So one of the famous algorithm you might have learned, you might have known is the banker's algorithm that will apply in the deadlock avoidance. Here, what will happen is whenever a new process come into the system and will make a new request into the system, so it will see the condition, the present condition of the system. If the present condition of the system allow that request, and after allowing it will be in a safe state, then only will allow the new request to enter into the system. Otherwise we just reject that particular request which is coming into the system. That is the philosophy behind deadlock avoidance. Next is the deadlock detection and recovery. So here we doesn't have the pre-checking algorithm, anything. So whatever new request coming into the system will allow the resources, and we say that you execute whatever resources you required, you take it and you execute it. But once the system go into the deadlock, once the deadlock has been detected, it will apply the recovery algorithm on it. So it will allow the deadlock to occur into the system. After that, it will make the recovery process. Now the next one is the deadlock ignorance. So here the system designer assume that in my operating system there will be no deadlock at all. Means in my I have made the operating system in such a way so that I will not get any deadlock into my system. So in such operating system, they will use the deadlock ignorance, in which they says that there will be no deadlock, so we'll ignore that particular deadlock, will not do any detection, will not do any recovery, will not do any prevention. We just assume that in my operating system there will be no deadlock, right? So that is the deadlock ignorance algorithm. It will ignore the problem as if it does not exist. So it assume that the deadlock not exists, is deadlock never exists into my system. So that is the philosophy behind deadlock ignorance. Here, there is a ostrich algorithm that will be used in the deadlock ignorance. Now, if we'll take, so you will ask like which particular method is good method, right? So all the method are good method. It depend upon two things actually. The first thing is what is the severity of the deadlock, means how severe my deadlock is, means once the system go into the deadlock, how much damage or how much severe damage it will do into my system. So the first is how much severe the deadlock is, or how much the effect of the deadlock is into my system. Okay. And the second is how frequently that deadlock is coming into my system. Okay. Let's take an example, real-time example. Okay. Let's assume that I am opening a new hospital And there is a scenario in this particular town, like once in a while, means let's say in 3 4 years, once there may be a power cut or power failure for 15 to 20 minutes. So if this is a scenario, do we have the prevention technique or avoidance technique? So which technique we'll use? Means if there is a frequency of the failure of the power is very less, let's say 15 minutes in 3 years or 4 years, so which particular method will apply here? So the method will apply here is, do we have to install the generator, or do we have to have the inverter on it, on the hospital? So the answer is the answer will ask to the first condition, that is how severe it is. Means if once in a while, means very rare, if there is a failure occur uh, into the power, and there is a ICU, and there are some critical patients are there, and they require ventilation support all the time, but there is a power cut for 15 minutes. So assume that all those ICU patients may die, right? So the severity or the damage by this particular failure is very high or very risky, right? So we'll use the prevention technique. Means we install the DG, we install the inverter in such a way that whenever there is a power failure, whether the frequency is very less, we apply the DG support into the hospital. Means we have to install the DG support into the hospital, so that uh, we can save those lives, right? So the criticality of the condition based on that. Now let's talk about the second condition. Second condition is, let's say there is a new school and there is a new school building, and the same thing will happen. Like in 3 years, there is a power failure of, let's say, 15 minutes. Do we require the prevention technique, or can we apply the avoidance technique? So the answer is, we here, if there is a 15-minute failure of the power in a school, so it is bearable, right? Instead of putting the whole bunch of DG for 3 years, only for 15 minutes in 3 year span of time, it's very costly, depend upon the application. So we'll not use the prevention technique here, right? So instead we'll not apply the DG on that, because the severity is very less. Means if there is a failure of 15 minutes in the school, what will happen? Nothing will happen, right? So depend upon the application to application, we can apply the deadlock prevention or deadlock avoidance technique. Because deadlock prevention technique, if it is applying, so the system has to check each and every request all the time. It has to execute all those prevention algorithm all the time. Means the cost is very high, right? But instead, if we'll apply other technique like ignorance, we'll ignore that there is a school and we ignore that particular thing. Then, but if the frequency is high, let's say there is a power cut of 4 hour or 5 hour every day, can we apply the ignorance algorithm even if it is a school? No, right? So we have to apply the prevention technique for that. Means we have to put the DG backup or inverter backup in the school if there is a power cut for 4 to 5 hours daily. So it depends upon the frequency. So it depends upon two things, that how frequently my deadlock is occurring into the operating system, and how severely it is damaging my means damaging the files or damaging something into the system. If it is a real-time system, then definitely I cannot afford the deadlock prevention, right? I cannot matlab, ignore the deadlock handling. Like if there is satellite launch, or let's say if there is a real-time operating system I'm using for very critical work, and if there is a deadlock for 1 second or 2 seconds, my whole system will fail and it will cost me more. So I'll use the deadlock prevention technique on that particular case. So depend upon application to application, we can apply any of the method to recover or to handle the deadlock, right? So let's see the first one, that is the deadlock prevention. Okay. Before that, let's talk about some concept which we'll use in these methods. Okay. So the first concept is called safe state. Means which particular state we can say is a safe state in my operating system. Okay. So when a process requests an available resource, system must decide if immediate allocation leaves the system in a safe state. Means let's say there is a process and this process is requesting the resource and the resource is available with us. But can we allocate that resource to that particular process immediately, or will apply some algorithm in such a way so that I'll wait that if I'll allocate the resource to that particular process, my system will be in a safe state. So I have to check that after giving this particular resource, my system should be in a safe state, right? So before giving that, I have to check it. That is happening in the deadlock avoidance. Now, what is a safe state? So the system is in a safe state if there exists a sequence. And what is the sequence? There is a sequence of process P1, P2 to Pn of all the process in the system, such that for each PI, means for each process, the resource that PI can still request can be satisfied by current available resource. Means the first condition of the safe state is if there is a process and it is requesting for a resource, so that resource will be fulfilled by my current available resources, means current remaining resources. Plus another condition is resources held by all the processes, that is all the older processes that we have to see. Means the available process and the resource which is handled by the older process. So the whole thing we have to see to give the resource to the newly coming or newly came process, right? So if there is a process, let's say if there is a process, let's say P1, P2, Pn. So P1 is the older one, right? P2 is also older. P3 is also older. Let's say come around P5 came. So P1 to P4 are the older one, right? So you assume that P5 is, let's say, the Pi, and these are all Pj, and this Pj, J is less than I. So that is the condition is saying. It says that if a new request came and it is requesting for the resource, I have to see how much resources are left and how much resources are taken by the older one. And based on that, I'll make the decision. For elaborating this, these are the thing. If PI resource or the new process resource need are not immediately available, then PI can wait until the PJ have finished. So I think you understood. Let's say if a newly process request for a resource, so will not allow it immediately if it is not available. So for that, what it will do, it will wait until PJ has finished. So once a older one has finished, it will release the resource and then new process will get it. Second is when PJ is finished, means the older one is finished, then newer one can obtain needed resources, execute, return allocated resources, and terminate. So this is the process this is a state of the process. We have seen that different states are there for the process. When Pi terminates, Pi plus 1 means the new one can obtain its needed resource and so on. So this is how it will work. Means The older one will be given more preferences to execute its resources. With the resources, it will execute everything, and then only it will release and terminate. If a system is in a safe state, means there is no deadlock. If the system is in unsafe state, there is a possibility of the deadlock. What is the meaning of avoidance? Avoidance ensure that the system will never enter into the unsafe state. So there is a safe state, there is an unsafe state. So safe state, no deadlock. And unsafe state, in the unsafe state, there is a part where there is a deadlock. It means that if we are going into the unsafe state, it doesn't mean that we are going into the deadlock. If we are in the unsafe state, there is a chance that we can go to the deadlock. Getting it? So there is a safe state, there is an unsafe state, and there is a deadlock state. There are 3 states. So the avoidance technique will make sure that you always be in a safe state, or the prevention is also ensuring that you are always in a safe state. Now, in the pictorial representation, a process will be represented by the circle. Resources, maybe there is a different instances of resources. Let's say there is a CPU. If CPU has 4 core, so 4 instances of CPU will be available. Getting it? So this is how we represent it. If process PI requests instance of RJ, means the resource. So this is the way how it will be requesting. And once PI is allocating the resource, this is how it will be allocated. Means there is a depend upon the arrow. If arrow is going from process to the resource, this is requesting. If the arrow goes from resource to the process, it is holding it. Okay. This is one graph that is called resource allocation graph. Here you can understand that there is a PI. P1. So there is a process 1 is requesting R1. R1 has only one instance, but R1, that is a resource 1, is already allocated to P2. There is an instance of R2. R2 has 2 instances. One instance has been allocated to P1 and one instance is already allocated to P2. P2 is requesting an instance of R3. R3 has only one instance, but R3 has already been allocated to P3. And there is a R4 which has 3 instances and all are free, never been requested nor been allocated. This is a simple resource allocation graph that will be useful for our detection and prevention process. So we'll see in the later section of this. This is another resource allocation graph. Here we doesn't have any deadlock. Here you can see there is a deadlock situation that may occur. What is the deadlock situation here? See, P3 is holding the resource R3. R3 is requested by P2. P2 is holding a resources R1, but R1 is requested by P1. So here P1 is requesting the resource which is already held by P2. P2 is requesting a resource which is already held by P3. Okay, already held by P3. Okay, so here we doesn't have any deadlock, because once we have the circular waiting type of thing, then only we can say there is a deadlock. But here there is no circular wait. P1 is waiting for P2 to release this so that P1 will work. But P3 is not waiting for anything. P3 is holding it. So definitely P3 is not requesting anything. P3 will do its execution and it will release the resources. Okay. So that is done in the P3. So P3 will release it. So P2 will get it. P2 will do all those things. P2 will release it. Then P1 will get it. So there is no deadlock. This is also an example where we doesn't have any deadlock or with a deadlock. So here we have the deadlock. You can see here P1 is requesting for R1, but R1 is held by P2. P2 is requesting for R3, it is hold by P3, but P3 is requesting by R2, which is hold by P1. So it is like this. P1 is requesting, which is hold by P2, and P2 is requesting, which is hold by P3, and P3 is requesting, which is again hold by P1, as you can see here, or P2. So in both the cases, there is a cycle. This is one cycle, this is another cycle. So in this case, there is a deadlock. And in this case, there is no deadlock. Okay. This is another wait for graph. Here we doesn't have any deadlock. Let's see. P1 is holding a resource of R1 and requesting for R2 and requesting for R1. R1 is already held by P2. So here you can see is P1 is requesting the resource which is held by P2 as well as P3, and P3 is requesting which is already held by P1 and P4. So as you can see here, we have this cycle, but there is no deadlock. Why there is no deadlock? See here, P3 is not requesting anything, so P3 will execute. Once it will execute, P1 will get all its resources. P1 will execute, then so P1 will execute, and then P1 will release all the resources, then P3 will execute, and then P4 is also not holding anything, not requesting anything. P4 can also execute its resources and release it, then P3 will execute it. So there is a situation of this, but there is no deadlock at all.